So today we start new chapter, line and plane. So first we discuss line. The concept of line we already studied in class 11. The chapter name is straight line, and in class 12 pair of straight line, but in Cartesian form. Here we have to discuss the equation of line in vector form. So for that, first we discuss how to determine the equation of line or how to determine a line. We determine a line if we know. Now here we always consider space because we consider three-dimensional system. So we use word space for representing a line. Now when we have to determine a line in space, we require one point on that line and a direction of that line. So first concept is equation of line. When point on line and direction is given. Now second concept is when we have to find the equation of line and 2 points on that line, then we can find the equation of line. Equation of line when 2 points on line is given. That means here we consider two concepts for determining the equation of line. First, when we know the point on that line and direction of that line, and second is when we know 2 points on that line. From that we can find the equation of line. Now see this diagram. We consider here line L. This line in space, because we consider here three coordinate system x, y, z. If this point P represented by the coordinate x, y, z, when we represent the equation of line L with respect to the position vector of this point P, suppose we consider here point P with respect to O as position vector r bar. That means when we represent the equation of line L in terms of this vector r, then that equation is called vector equation of line. And when we represent the equation of line L in terms of x, y, z, then that equation we call Cartesian equation. So we have to see different types of equation of line in vector form. Now see the first type, vector equation of line passing through a given point and parallel to the given vectors. That means when one point on that line is provided, suppose that point is A and position vector of that point is A bar. Now and vector parallel to this line is given, suppose that vector is vector B bar. Now here we have to find the vector equation of line passing through a point A of A bar and parallel to the vector B bar. So theorem based on this first type is, see, the vector equation of a line passing through the point A of A bar and parallel to the vector B bar is r bar equals to A bar plus lambda into B bar, where lambda is a scalar. So this theorem we have to prove. So for that we consider a line passing through a point A of A bar, and we consider a vector B bar which is parallel to this line L. So we have to write here proof. So first we draw this figure. We consider a line L. This line L pass through the point A and position vector of this point A with respect to origin is A bar. So we consider here position vector of this point A with respect to O. With respect to O, and this point P be any point on that line, and position vector of this point P we consider r bar with respect to origin O. let L be a line in space passing through A of A bar and parallel to B bar. Because we have to find the equation of line passing through the point A of A bar and parallel to the vector B bar. So we consider here line L, which is passing through this point A. So we consider here position vector of this point A as A bar with respect to origin O. So we consider point P on line L other than A. Now we consider here point P on this line L other than A, and position vector of this point P we consider as R bar. So we write here, let position vector of point P with respect to O is R bar. Now these 2 points A and P lie on this line L. That means vector AP is parallel to this vector B bar. Therefore, vector AP is parallel to vector B bar. Because line is parallel to the vector, so this vector AP is also parallel to this vector B bar. Therefore, AP and vector B are parallel vectors, and we know that when two vectors are parallel, then there exists a scalar. So we write here, therefore there exists scalar lambda such that vector AP is equal to lambda into vector B bar. So we write here position vector of AP as R bar minus A bar. R bar minus A bar is equal to lambda B bar. So from this we write R bar is equal to A bar plus lambda into B bar. This is vector equation of line when that line pass through the point A of A bar and parallel to the vector B bar. Now see, theorem second, the Cartesian equations of the line passing through A of x1, y1, z1 and having direction ratio ABC are x minus x1 upon A is equals to y minus y1 upon B is equals to z minus z1 upon C. So in theorem first, we find equation of line passing through the point A of A bar and parallel to the vector B bar. Here, instead of that, the position vector of point A, the coordinate of that point A is provided and the vector parallel to the given line. So instead of that, the direction ratio of that line is given. So we have to use here concept when we have to find the direction ratio of a line passing through 2 points, or when we have to find the direction ratios of a vector passing through 2 points, then we use the concept x2 minus x1, y2 minus y1 and z2 minus z1. So this x2 minus x1 is A, y2 minus y1 is B, z2 minus z1 is C. That means when we know the 2 points on given line, then we can find the direction ratio of that line by using the concept A equals to x2 minus x1, B equals to y2 minus y1, C is equals to z2 minus z1. And one more concept we know, when two vectors are parallel, then their direction ratios are in proportion. So we use this concept when two vectors are parallel, suppose vector A and B are parallel, then their direction ratios are in proportion. Now see here, we have to find the Cartesian equation of line passing through the point A of x1, y1, z1. So we consider here line L which pass through the point A of x1, y1, z1, and we consider one more point on that line, that is P, So we consider here coordinate of point P as x, y, z. So we first find the direction ratio of this line L in terms of x and x1, y and y1, z and z1. So right here in proof, let line L pass through the point A of x1, y1, z1 having direction ratio small abc. So we consider one more point on line L other than A. So we write here, let P be any point on line L other than A. So we consider here point P. You can write P equals to x, y, z. So we consider coordinate of point P as x, y, z. Now we have to find the direction ratio of line L. Therefore, the direction ratio of line L is, we write here by using the formula x2 minus x1 is, we get here, in place of x2 we have value x, so we write here x minus x1. In place of y2 we have y, so we write here y minus y1, and third is z minus z1. So in this way we get the direction ratio of line L when we consider 2 points A and P on that line. So this direction ratio and given direction ratio ABC are of the same line. So we write the concept of when two vectors are parallel, then their direction ratios are in proportion. So we write here x minus x1 upon A is equals to y minus y1 upon B is equals to z minus z1 upon C. If you observe, actually this is 2-point form. That means when we consider point P as x2, y2, z2, then we get here x minus x1 upon x2 minus x1, y minus y1 upon y2 minus y1 is equals to z minus z1 upon z2 minus z1. When we know the coordinate of point P, which we consider other than this x, y, z as x2, y2, z2. So this is actually 2-point form, but here we consider the Cartesian equation of line passing through A of x1, y1, z1 and having direction ratio ABC. So we have to prove in this way the theorem second. This is also called symmetric form. This is also called symmetric form. Now see second form, vector equation of line passing through two given points. So in first theorem we see vector equation of line passing through a point and parallel to the vector B. So here we have to find the vector equation of line passing through 2 points. Suppose that 2 points are point A and B. So we consider here point A whose position vector is A bar, then second point B whose position vector is B bar, and on this line we consider one more point other than AB as point P. So the position vector of that point P we consider R bar. So we consider position vector of this point P with respect to origin O as R bar. So theorem based on this vector equation of line passing through two given points is, now see this statement, the vector equation of line passing through the points A of A bar and B of B bar is R bar equals to A bar plus lambda in bracket B bar minus A bar, where lambda is the scalar. So first we have to consider here a line L which is passing through the point A of A bar and B of B bar, and we have to consider one more point on this line other than AB, which is point P. So we write here in proof let line L pass through the points A of A bar and B of B bar. Let P of R bar be any point on line L other than A and B with respect to origin O. Now we consider point A with position vector A bar, point B with position vector B bar, and point P with position vector R bar with respect to origin O. Now if you observe this diagram figure, this AB and this AP lie on same line. That means if we consider the vector AB and vector AP, both the vector lie on same line. That means this one vector can be written in the scalar multiple of second. So we write here, therefore vector AP is equal to lambda into vector AB, where lambda is scalar. Therefore this AP bar can be written as R bar minus A bar. Lambda into this vector AB bar can be written as B bar minus A bar. So we write this as R bar is equal to minus A bar. After transferring to right hand side we get plus A bar plus lambda in bracket B bar minus A bar. So this is vector equation of line passing through the point A of A bar and B of B bar. Now see next theorem, the Cartesian equations of a line passing through A of x1 y1 z1 and B of x2 y2 z2 is x minus x1 upon x2 minus x1 is equals to y minus y1 upon z2 minus y minus y1 upon y2 minus y1 is equals to z minus z1 upon z2 minus z1. So instead of position vector of this point A, B, we have provided the coordinate of that point, that means Cartesian form. So we consider here one more point on this line on which this point AB lies. So we consider point P other than AB. So we write here, let P of xyz be any point on a line passing through A of x1 y1 z1 and B of x2 y2 z2. Now since these 3 points lie on the same line, we get two vectors, vector AB and vector AP. That means we can find the position vector of AB, that is direction ratios of this point AB. So we write here, direction ratio of AB is, so by using the concept x2 minus x1, y2 minus y1, z2 minus z1, we find the direction ratios of AB. So direction ratio of AB, we get x2 minus x1, y2 minus y1, z2 minus z1. So we write here x2 minus x1, y2 minus y1, z2 minus z1. And AP, so we write a direction ratios of this AP is, so we get direction ratio of AP, which is here instead of x2, y2, z2 we have x, y, z. So we write here x minus x1, y minus y1, z minus z1. Now AP and AB both lie on same line, so their direction ratios must be same, and we write that in proportion. So we write here, now since this point A, B, P are collinear, therefore their direction ratios are same. So we write here x minus x1 upon x2 minus x1 is equal to y minus y1 upon y2 minus y1 is equal to z minus z1 upon z2 minus z1. So this form we call Cartesian form because we use Cartesian coordinate of the given 2 points. So this formula we use for solving the problems, that means for finding the equation of line when that line pass through 2 given points.